Biot-Savart Law. So now we're going to calculate the magnetic field due to a current, usually the current flowing through a conductor like a wire. And this is a calculus equation, or this is an equation that's based on not only a lot of calculus, but also has a vector nature to it. So let's look at the most general form. We're not going to really use the full vector form right here because it's really difficult to use. But we'll look at the full vector form of this first of all. Then we'll go to the non-vector calculus form. But again, our goal here is to calculate the magnetic field due to a wire. We will, in later sections, actually reduce this to an algebraic expression so we don't have to worry about the calculus aspect. But looking at this, dB represents an infinitesimal amount of magnetic field, or the magnetic field contribution due to an infinitesimal length of wire. So really, if I'm calculating the total magnetic field at this location, I have to add up all the little dBs at that particular place due to each infinitesimal length of wire as we put them all together. Okay? So we're going to have to actually integrate this whole expression to calculate the magnetic field. But if we look at this, let's analyze what exactly is in this equation. We have mu 0, the permeability of free space, it's a constant. We have 4 pi, another constant down there. I is the amount of current. So what this assumes, obviously, is the current is constant throughout the wire. And really, from Kirchhoff's junction rule, we know unless we're branching current off, that a single strand of wire is going to have a constant current, so we don't have to worry about that. That I is pretty much the same throughout the wire. dl, again, represents an infinitesimal length, so we're taking this in the limit where dl goes to 0. dl is a vector. It points in the direction that the wire is going. So dl cross r hat, it's a unit vector. It doesn't have any value to it, it's a unit vector, but it points in the direction of the magnetic field that we're calculating. So if we're doing a cross product here, dl cross dB, we can see that the magnetic field would actually point into the bore. Again, we'll get away from this vector nature right here. With many of the equations, we see it's an inverse law, okay? 1 over r squared. It's proportional to 1 over r squared, I should say. It's an inverse square law. So again, this is the most general form. This is the most complete form of this equation. Again, doing vector calculus is quite a bit of a challenge. So we're going to separate this, and instead of looking at just the vector form, vector calculus form, we're going to calculate the magnitude of the vector first, and then we're going to go back and figure out the direction. Did you see what I did here? I actually used the right-hand rule to obtain the direction. So find magnitude first, then we'll actually apply the right-hand rule to find the direction, which is easier than keeping everything in its vector form. Okay, so here is the magnitude. Here we got rid of the vector form of this. We just have to be a little bit careful here because we have to understand what this sine theta represents. Remember, we had dl cross r hat. So this angle represents the r vector, the distance vector, the position vector, whereas dl represents the direction that the wire is going. So, again, theta is the angle between these two. When we're right, perpendicular to this magnetic field, sine 90 degrees gives us, its maximum value, it's 1. As we go further and further down the wire, that angle is going to get further and further away from 90 degrees and begin to approach 0 degrees. So further away from the wire, r squared is going to become larger and larger, sine theta is going to become smaller and smaller, and the more distant contributions are going to be not as significant for this magnetic field. Okay, so again, here is our equation for an infinitesimal contribution to the magnetic field due to an infinitesimal section of this wire. So, if we want to put all the contributions of the total wire together, that's the whole idea of integration, right? Adding an infinite number of infinitesimal parts together. We integrate both sides of the equation, and if we want to keep it still in the vector form, it would look something like this. If we want to just calculate the magnitude of the vector, which is preferable, it just makes things a lot easier, then it looks like this. Okay? Again, recognizing that sine theta, theta represents the angle between our position vector and the vector pointing along the length of the wire. Okay? Still challenging. So again, for this course, we are going to use this law to derive some simpler cases. You know, a lot of times in physics, we'll introduce something in its most general form using calculus, and then we'll use the calculus to come up with an easier algebraic expression to solve. And that's certainly what we're going to do here. We're going to look at this law for a single wire. We'll do the same for a loop. You can do the same for a solenoid and get an expression for the magnetic field. Okay? If you do want to use this particular law, you can use it in a more powerful way to do numerical analysis using a computer. Again, you know, with calculus, the idea is to take this infinitesimal section and the limit that goes to 0. If we do a computer calculation of this, obviously we can't go to an infinitesimal size. We go to very, very small sizes to get accurate computations.